Hi, today I'm discussing electronic structure of atom. The chapter 6 I'm gonna give you in two videos. First one, the overall idea of chapter 6. We begin chapter 6 with electronic structure of atoms. We talk about properties of waves, and waves has properties including this is a wave. Wave has properties like lambda, frequency and speed. All the electromagnetic waves, they have the same speed, which is 3 into 10 to the power negative 8, 3 into 10 to the power 8. And then very first equation in this chapter we are coming is the relationship between wavelength and the frequency. This is the important equation, which is mu is frequency equals c over lambda. Mu frequency, c speed of light, wavelength. This is very important equation you need to know. And then what is the relationship between the frequency and the wavelength? Frequency is number of waves passing in per unit time. So the higher the frequency, higher the energy. Higher the frequency, higher the energy. Similarly, higher the frequency, sign for the frequency is mu. It is mu. Higher the frequency, higher the energy. But if you think about frequency and wavelength has inverse relationship. In other words, higher the frequency, lower wavelength. Lower the wavelength. So this is the very first equation, mu equals c over lambda. With that, there is a question. Calculate the wavelength in nanometers of the red light emitted by a barcode scanner that has the frequency of 4.62 into 10 to the power 14. In this question, you have to calculate the wavelength. I think you can see it. Let's see. It is example 3.1. Calculate the wavelength in nanometers of the red light emitted by a barcode scanner. So it has given the frequency, which is mu. I know mu is 4.62 into 10 to the power 14 per second. And then c, speed of light, is constant throughout all the electromagnetic radiation, which is 3 into 10 to the power 8 meters per second. I am asking lambda. I know my equation mu equals c over lambda. I know mu, frequency. I know my speed of light. I can find lambda. I substitute these terms. 4.62 into 10 to the power 14 equals c is 3 into 10 to the power 8 meters per second. This is per second. I can find the lambda. So my lambda is, I am taking lambda to the other side, and then 3 into 10 to the power 8 meters per second, you divide both sides by 4.62 into 10 to the power 14 per second, and it's giving me the answer as 6.49 into 10 to the power negative 7 meters. But they asked the question in nanometers. The relationship is 1 meter equal to 10 to the power 9 nanometers. So I have my answer, 6.49 into 10 to the power negative 7, 10 to the power negative 9 meters equal to 1 nanometer. My answer is 649 nanometers. So this is the very first equation we are learning, mu equals c over lambda. With that, we are moving to our next, the electromagnetic spectrum. Electromagnetic spectrum is important. You need to know the order of electromagnetic spectrum and the visible light. You need to know the color order of visible light. Example like this is 400, this is 750. The 400 is smaller, the wavelength, which is highest frequency. In 400, which color you can see? In 400, you can see the purple color, while in 750, you can see red color. You need to know, so the electromagnetic radiation start with gamma rays, which has smallest wavelength, highest energy. This is high energy. This is low energy. You need to know the order, like radio waves, after radio waves, microwaves, infrared, IR, visible also. You need to know the order of colors, Roig Bay, red, orange, yellow, green, blue, indigo, violet, right? Roig Bay. So you need to know these, or you need to know the order. And then if I ask you, I'm not going to ask you to memorize the frequency, but you need to know the order. And with that, we are moving to the photoelectric effect. You need to know the photoelectric effect. Photoelectric effect talk about when light strikes on the metal surface, light emits electrons. So the light, so this is the metal surface, light strikes on the metal surface, electrons will be emitted. When the light strikes on the metal surface, this is the metal surface, electrons will be emitted. So in order for the electrons to be emitted, the incoming light, this is light, incoming light should transfer quanta of energy to the metal surface. In that way, they call the light is quantized. With that, we are coming to our next equation. E equals h mu. E is energy, h Planck's constant, mu is frequency. This is the second equation. No need to memorize Planck's constant. I am giving you the Planck's constant. But this is the equation. Planck's constant is 6.626 into 6.626 into 10 to the power negative 34 joule second. This is the second equation we are learning. And then there is a question. Calculate the energy of photon. Calculate the energy of one photon of the yellow light that has the wavelength of 589. At that time, how you need to approach this problem. This is a 6.3. Calculate the energy of one photon of yellow light that has the wavelength of 589. You have to calculate energy, so you know you need to use E equals h mu equation because it's associate energy. That's how you know you need to use that equation. But this equation is only frequency. How do you relate this one to wavelength? We know mu equals c over lambda. So you can substitute E equals h c over lambda. You have to find energy. You know h is 6.626 Planck's constant. 10 to the power negative 34 joule second. C is 3 to 10 to the power 8 meters per second. Lambda is given 589 nanometers. You need to convert nanometers to meters. 1 meter equal to 10 to the power 9. So 589 into 10 to the power negative 9 meters. So it gives you the answer. So that's how you do this question. And then atomic emission, we're going to discuss about atomic emission. And then you're coming to the hydrogen spectrum. Hydrogen spectrum is important. Another important technique is hydrogen spectrum. So in hydrogen spectrum, what is spectrum? Spectrum means in hydrogen has one electron. One electron in hydrogen, when it goes to excited energy states, it absorbs energy. Think about hydrogen atomic levels. Hydrogen has first shell, second, like first principal shell, second principal shell. Example, if I take the hydrogen nucleus, this is the hydrogen nucleus. So hydrogen nucleus has one proton, one proton, and around the hydrogen there's principal energy shells, right? This one electron absorb energy, go to the higher energy shells, and that time the higher energy shells is very unstable, so it slowly release that energy and come to lower energy states that call electron relaxation. That energy falls into the visible range. We see it in colors. That's what we call the spectrum. So absorbing we call electron excitation. When it comes to the lower energy state, we call electron relaxation. It comes to the lower energy states. So this is the ladder diagram, like this is the circular diagram. So but if I draw in this way, so this is the nucleus, first energy shell, second energy shell, like that. So the electron is in the closest shell, it absorbs energy, go to the high energy shells. This is called electron excitation. When it comes to the lower, this electron come to the lower energy states, it releases energy. We call this is relaxation. Okay. Sorry about that. Electron excitation and electron relaxation. So with that, there is how to calculate the two different energies of the two different levels. So always you need to keep in mind. So this is the energy diagram in the Bohr model. So always when you go away from the nucleus, energy each, so we call it principal energy shell 1, n equals 2, n equals 3. This electron can stay only in the specific energy shells. The electron cannot stay in between. So electron always need to absorb certain exact quantity of energy to go to the higher energy states. We call this closest energy states ground state, and higher energy states excited states. Excited states. So high energy is the ground state and excited state. Always electron goes from ground state to excited state. Always in order for the electron to go from ground state to excited state, it need to absorb energy. That call electron excitation. From the high energy states to the lower energy states, electron need to release energy. That call electron relaxation. And one more equation I want to show you before we wrap up the first section, which is how do you calculate the energy between two energy states. For that I have this equation, which is another important equation. So delta E, you know now delta is difference, right? Delta E is if energy difference equal E final minus E initial equals negative 2.18 into 10 to the power negative 18, 1 into n final squared minus 1 into n initial squared. So this is the equation to calculate the energy for a specific transition. So again, this equation is delta E, energy difference, equals E final state, energy of the final state, minus energy of initial state equal negative 2.18 into 10 to the power negative 18, 1 into n final squared minus 1 into n initial squared. So this is the equation. Example, if electron moves, so this is the energy states, ground state, n equals 1, n equals 2, n equals 3, n equals 4. Okay, so my electron transfer from, just imagine it jumps from, it was excited, it was already there, it came from 4 to 2, right? So when it relaxed from 4 to 2, my initial state is Ni is 4 and final is 2. So if I apply my values to this equation, E delta E equals E final minus E initial, negative 2.18 into 10 to the power negative 18 n final, 1 into 2 squared minus 1 into 4 squared. So negative 2.18 into 10 to the power negative 18, 1 into 4 divide 1 into 16. You solve this equation, you can find the energy for that particular transition. So in order to wrap up this section, we learn mainly three equations. Mu equals C over lambda. Mu is frequency. Mu equals C over lambda. Mu is frequency. C is speed of light. Lambda is wavelength. Frequency, speed of light, lambda is wavelength. Okay. And then we learn E equals h mu. E is energy for the particular transition. H is Planck's constant. Mu is frequency. Lastly, we learn energy for a specific transition. Delta E equals E final minus E initial equals negative 2.18 into 10 to the power negative 18. 1 in final minus squared in initial squared. So this is the three equations we learned so far. Thank you.